You might expect hydration of alkynes to produce an enol, where we add the hydrogen here and the hydroxyl group here, and you get this thing that has a carbon-carbon double bond and a hydroxyl group. The enol is actually an intermediate, but it immediately tautomerizes to become a carbonyl. The CO double bond is so much stronger than the CC double bond that the carbonyl is favored over the CC double bond. Thus, the end result of a Markovnikov hydration of a carbonyl is a ketone, and of anti-Markovnikov hydration, an aldehyde. Let's look at some details. Acid-catalyzed hydration gives you Markovnikov hydration, which is going to give you the ketone. The reagents that you use are sulfuric acid, water, and mercuric sulfate. The mercuric sulfate, this is not the same as oxymercuration, demercuration. Let's look at the mechanism. We need to create a cation in a vinylic position, which is very unstable unless you have that mercury ion. So in the first step, our pi bond of our alkyne attacks the mercury to give this adduct with the vinylic cation. Water can then do nucleophilic attack at the vinylic cation. Again, this vinylic carbocation cannot form without the mercury being present. So, once the water does nucleophilic attack at the vinylic cation, we end up with this protonated alcohol. So we need to deprotonate it. And another water molecule can act as a base and do proton transfer. And now we've taken away that proton. Now we just need to make the mercury go away. The pi bond acts as a base to do proton transfer on hydronium that's present from the sulfuric acid, which then creates this carbocation, and the carbonyl is formed by resonance, and that takes back that pair of electrons that was binding the mercury. And so we end up with the enol. But this is immediately going to tautomerize to become a ketone. Here's acid-catalyzed tautomerization. First, the pi bond of the enol acts as a base, protonating. We end up with a carbocation on the alpha carbon of the resulting alcohol. So that forms a carbonyl in this resonance structure. And then water acts as a base to deprotonate the oxygen, and you end up with a ketone. Hydroboration oxidation gives us the anti-Markovnikov enol, which then becomes an aldehyde. But instead of using borane, we use a dialkyl borane, right? Like having two alkyl groups. In this case, two cyamyl groups. This is dicyamyl borane, or 9-borobicyclo 3.3.1 nonane. These are both what we call R2BH dialkyl boranes. And this prevents a second addition, which we don't want when we're using alkynes. So here we have our terminal alkyne, and we react it first with 9-BBN or dicyamylborane. That's the hydroboration step. And then in the oxidation step, we use hydrogen peroxide and sodium hydroxide, and that's going to form hydroperoxide ions. And this produces our Anti-Markovnikov enol, which then tautomerizes to form an aldehyde. Now, this is not acidic conditions, so the tautomerization takes place via a different mechanism. First, hydroxide deprotonates the hydroxyl of the anti-Markovnikov enol. Now we have what's called an enolate, which has a resonance form that is carbonyl with a carbanion. Now this is the less stable resonance form. However, this carbanion can get protonated by water, and we end up with an aldehyde. Just summing up, if you use sulfuric acid, water, and mercuric sulfate on an alkyne, that's acid-catalyzed hydration. And you end up with a ketone that is the Markovnikov product. If we use dialkylborane followed by peroxide and hydroxide, that is hydroboration oxidation. Which gives us an aldehyde that is the anti-Markovnikov product. Which set of reagents would we use to accomplish this transformation?